back to the Whispers of Deep Time. In the last two episodes, we examined cosmology and Genesis. Today, we turn to a specific and measurable question. How does science determine the age of the Earth? Well, it's not philosophically or symbolically. It's done quantitatively, using empirical methods. We're going to look at the methods that are used, the assumptions that are involved, how those assumptions are tested, and how should Christians evaluate the conclusions. Today we'll walk step by step through the empirical science of dating techniques and look at their limitations. For most of Western history, estimates of Earth's age were based on biblical chronologies. Archbishop James Ussher famously calculated a creation date of 4004 BC. That estimate reflected the interpretive tools available at the time. But beginning in the late 18th century and the early 19th centuries, geologists like James Hutton and Charles Lyell observed something unexpected. Earth's surface features required immense spans of time to form. River erosion rates, sediment accumulation, mountain uplift, these processes all operate very slowly. The scale of observed geological formation suggested durations far exceeding the thousands of years previously noted. By the early 20th century, physics had introduced something very revolutionary, the idea of radioactive decay being able to date the rock structure. And that changed everything. Taken as infallible, it has become the standard in geological dating. At the atomic level, certain isotopes are unstable. Over time, they spontaneously decay into different isotopes at predictable rates. These rates are expressed as half-lives, the time required for half of a radioactive isotope to decay. For example, uranium-238 decays to lead-206. It has a half-life of 4.47 billion years. Potassium-40 will decay into argon-40. Its half-life is 1.25 billion years. These decay rates have been measured in laboratory conditions and are governed by fundamental physical constants. When molten rock crystallizes, radioactive parent isotopes are incorporated into minerals. From that point forward, decay begins accumulating daughter isotopes. By measuring the ratio of parent to daughter isotopes, scientists solve the decay equation. By using the decay constant, the daughter isotope quantity found in the sample, and the remaining parent isotope, the calculation produces the age since crystallization. Importantly, this is not calibrated against evolutionary assumptions. It's derived from measurable atomic physics. Radiometric dating is not infallible. The dating technique depends on three major assumptions to begin with. The first being that decay rates have remained constant. The second is that the system remained closed. And third is that the initial daughter quantities can be accounted for. So let's examine each of these assumptions. The first is the stability of decay rates. They depend upon nuclear forces. Experimental attempts to alter them through temperature, pressure, and chemical conditions have produced negligible changes. In order for decay rates to shift dramatically in the past, fundamental constants would have needed to change, which would also alter stellar processes and atomic stability. Astrophysical observations of different stars and supernovae show decay signatures consistent with present rates across vast distances, effectively across time. In closed systems, minerals like zircon are particularly valuable because they strongly incorporate uranium but exclude lead during formation. If lead is found within a zircon crystal, it is overwhelmingly likely to be radiogenic or formed from decay itself. Additionally, multiple isotopic systems can be applied to the same rock. If different decay chains converge on the same age, it increases confidence that the system remained closed since formation. One problem with radiometric dating is determining the additional conditions. Isochron dating was developed specifically to address unknown initial daughter isotopes. Rather than assuming zero initial daughter content, scientists analyze multiple samples from the same rock body. If the isotopic ratios form a linear correlation, which is the isochron, the slope provides the age without assuming initial daughter absence. This reduces circularity significantly. However, the age of the Earth is not determined by a single technique. Multiple independent lines of evidence converge. Radiometric dating of terrestrial rocks, the dating of lunar samples, dating of meteorites, particularly chondrites, stellar evolution models, and white dwarf cooling rates. Meteorites provide especially important data because they formed during the early solar system and have not undergone geological recycling like Earth's crust. They preserve early isotopic signatures. Radiometric dating of meteorites consistently yields ages of around 4.4 billion years. Lunar rocks return similar ages. The oldest terrestrial zircons found in Western Australia date to about 4.4 billion years ago. The convergence is striking. Different materials, different isotope systems, different laboratories, all similar ages. That convergence is why 4.54 billion years is widely accepted by science. Even apart from isotopes, Earth's structure reflects long duration. Consider the thickness of sedimentary rock layers worldwide, coral reef growth rates, ice cores from Antarctica and Greenland containing seasonal layers extending hundreds of thousands of years, plate tectonics moving continents just centimeters per year. At current rates, continental drift alone requires tens to hundreds of millions of years to produce present geography. These are not isolated data points, they're cumulative. However, there are anomalies. For example, the white sand footprints found in sandstone along the ancient Lake Otero and the Tularosa Basin in New Mexico. They're estimated at 22,000 years old, and it proved man was in America earlier than the Clovis people. The London Hammer, found encased in solid rock in 1936, shows rock formation in as little as a few hundred years. While anomalies exist, it does show that there are certain conditions that allow rock formation to occur in far less time than others. In everything, there are objections to certain findings. Some Christians argue that decay rates may have been accelerated during events like the flood, and there are certain possibilities. However, accelerated decay sufficient to compress billions of years into thousands would release enormous heat, enough to melt Earth's crust multiple times. Others suggest isotopic inheritance or contamination, and it is possible. While contamination can occur, it tends to produce discordant results, not the remarkable agreement observed across systems. Scientific practice includes discarding anomalous data and testing repeatability across labs. The existence of technical objections is important. They sharpen methodology, but objections must also explain the convergence of independent models. So, what does this mean for faith? If Earth is 4.54 billion years old, does that undermine Christianity? Definitely not. But is the science correct? We know that rock can form in as little as 50 years, so did it take billions of years? Christian faith affirms a creator or designer, creation as contingent, humanity as image bearers, and the reality of sin and redemption. None of these doctrines specify a numeric age. Historically, the Church has included diverse views on Genesis interpretation, literal 24-hour days, day-age views, framework interpretations, and analogical days. The age of the earth becomes problematic only if a specific reading of Genesis is made non-negotiable. The scientific evidence itself does not argue for atheism. It argues for duration. Duration is not a theological claim. It is a physical measurement. Remember that science measures processes. It does not assign ultimate meaning. Radiometric dating can determine when zircon crystallized. It cannot determine why existence exists. If anything, the reliability of physical constants may support a theistic worldview, suggesting an ordered cosmos governed by consistent laws, inferring a designer. The deeper philosophical question is not how old is Earth? It is, why is there a universe governed by mathematically stable laws in the first place? Science describes regularity. Theology asks about grounding. These questions operate at different explanatory levels. Okay, now let's summarize clearly. Radiometric dating is grounded in measurable nuclear physics. Multiple isotope systems cross-validate results. Meteorites, lunar samples, and Earth's oldest minerals converge on an age of 4.54 billion years, give or take. Geological processes independently support long durations. The Earth's age by itself does not negate Christian doctrine. Christians are free to wrestle with interpretation, but intellectual integrity requires us to understand the data accurately before responding to it. Deep time is not a theological opponent. It is a scientific conclusion that's drawn from multiple independent measurements. Next episode, we will examine biological history and ask, how does age and the genetic evidence inform our understanding of life's development? And can evolutionary mechanisms be reconciled with providence? The Whispers of Deep Time is an initiative that serves as a strategic bridge where the rigor of empirical discovery meets the depths of sacred tradition. For too long, the opening chapters of Genesis have been reduced to a cultural and scientific battleground, where the rigid demands of literalism clash with the overwhelming evidence of geology and cosmology. Until next time, this is Alan saying goodbye.